Lastly, let's consider an example of a pump. A pump draws water with a mass flow rate of 9 kilograms per second through a piping network with a velocity of 3 meters per second. The inlet pressure and temperature of the water into the pump is 100 kPa and 25 degrees centigrade respectively. At the exit of our piping network, our pressure has increased to 140 kPa, whereas the temperature has remained the same. Our exit velocity is 12 meters per second. The exit is located 15 meters above our inlet. We want to determine our pumping power required to operate this pump under this configuration in units of kilowatts. We start by writing our state variables. At state 1, our pressure is 100 kPa, our temperature is 25 degrees centigrade, our mass flow rate is 9 kilograms per second, our velocity is 3 meters per second, and we will set our inlet as a reference elevation of 0 meters. At state 2, our pressure has increased to 140 kPa, our temperature is the same as our inlet, our mass flow rate at our exit is the same as our inlet, our velocity has increased to 12 meters per second, and our elevation is now taken as 15 meters. We begin by writing the conservation of energy equation for a single stream steady state device. dEdt is equal to 0, which is equal to Q dot less W dot, plus our mass flow into our system carrying an enthalpy, kinetic, and potential energy, less our mass flow out of our system carrying an enthalpy, kinetic, and potential energy. Under this particular formulation, we cannot neglect our change of potential energies. However, we will neglect any heat transferred to or from our system. Rearranging our conservation of energy equation for our work into our system, we find that negative W dot is equal to M dot times the following quantities: H2 less H1 plus V2 squared minus V1 squared over 2 plus G times the quantity Z2 less Z1. We know our difference of elevation as 15 meters. We know our inlet and exit velocities, and we know our mass flow rate. The only thing we have to determine is our enthalpy at our inlet and exit of our system. Now let's consider the following. Our enthalpy at state 1 can be taken as our saturated liquid specific enthalpy. Thus our enthalpy at state 1 is 104.87 kilojoule per kg. However, if we try to solve our enthalpy at state 2 using our saturated liquid specific enthalpy, we would find H2 would be identically equal to H1, and thus their difference would be equal to 0. We know, however, there is going to be a slight difference of enthalpy within our system. Thus, if we recall the definition of enthalpy as a function of temperature and pressure for an incompressible substance, H is approximately equal to our saturated liquid specific internal energy evaluated at our temperature of interest plus our pressure times our saturated liquid specific volume evaluated at our temperature. Thus, our difference between our enthalpies at state 2 and state 1 can be evaluated as our following expression. We recognize our saturated liquid specific internal energies evaluated at T2 and T1 are going to be identically equal. Terms cancel out. Thus, we take our saturated liquid specific volume from table B.1.1 as 0.001003 meters cubed per kg. Now we can begin to substitute values into our conservation of energy equation, ensuring proper units. Negative W dot is equal to our mass flow rate, 9 kilograms per second, times the following quantities. The first is our difference of enthalpies. This is our saturated liquid specific volume, 0.001003 meters cubed per kg, times the difference of pressures between state 2 and state 1, i.e. 140 minus 100 kPa, plus the difference of our kinetic energies. We have our velocity at state 2, 12 meters per second squared, less our velocity at state 1, 3 meters per second squared over 2. And to convert this to our proper units, we have to divide by a factor of 1,000 such that we get kilojoule per kg. Last but not least, we have to include our change of potential energy within our system. We'd have our gravitational constant, 9.81 meters per second squared, times our change of elevation, 15 meters, and once again we have to divide by a factor of 1,000 such that we have units of kilojoules per kg. Therefore, negative W dot would be equal to 2.41 kilowatts, i.e. we need to supply 2.41 kilowatts